Dear students, welcome to the problem solving session on Cauchy integral formula part 4. In the first few videos, we see the basics and then we started solving few problems on Cauchy integral theorem and Cauchy integral formula. At first, we have evaluated simple problems which consist of only one singular points. And in the next video, we started evaluating problem consists of two singular points. At example 4, both the singular point lies outside. In the next example, one singular point lies inside and the other singular point lies outside. And in example 6, we see both the singular points lies inside. In all these examples, we notice that my region is simply mod z is equal to some radius r. Immediately, I can write my center as 0, 0 and the radius as the given number r. For example, like 1 by 2, 3 by 2, 3 etc. So we easily draw the figures. From the figures, we can easily find whether my singular points are lying inside or outside C. In the next problem, we took some different region. It is look like modulus of z minus a is equal to r, where a is any complex number. In this case, it is not guaranteed that my center lies at 0, 0. So we solved this kind of problems and we can see the different region. Similarly, we did one more example with modulus of z minus I equal to 2. One more thing we have to note, in all our problems, my singular points are real numbers. Easily I can find the singular point. So in this session, we are going to deal with a problem whose region also little complicated and the roots are going to be complex. Let us see the example. Integral over C z plus 4 divided by z square plus 2z plus 5 dz, where the region is modulus of z plus 1 plus I equal to 2. By seeing the question, it is very obvious we can say the singular points are going to be complex. Let us solve the problem. As usual, step 1 is my given region. Modulus of z plus 1 plus I is equal to 2. Substitute the value of z, that is x plus iy plus 1 plus I equal to 2. Now rearranging the real and imaginary parts, we get x plus 1 plus I into y plus 1 is equal to 2. We know the formula. Modulus of a plus ib is equal to square root of a square plus b square. Therefore, square root of x plus 1 whole square plus y plus 1 whole square is equal to 2. Squaring on both sides, we get x plus 1 whole square plus y plus 1 whole square is equal to 2 square. We know the general form of circle, x minus a whole square plus y minus b whole square is equal to r square. Comparing these two, we can easily write the center as minus 1 comma minus 1, radius is 2. Now let us draw the diagram. Center is minus 1 comma 1 and radius is 2. So I can mark the point as 1 comma minus 1. In the y-axis, if it moves 2 points up, it is going to be minus 1 comma 1. So we can easily draw the circle and mark the radius. Step 2, we are going to find the singular points. Equate the denominator to 0. Now this looks like a complex root, so we are going to use the formula z equal to minus b plus or minus square root of b square minus 4ac divided by 2a. So the general form of the quadratic equation is az square plus bz plus c equal to 0. Comparing with our problem, a equal to 1, b equal to 2 and c equal to 5. Now substituting the values here, we get z is equal to minus 2 plus or minus b square is 4 minus 4 into 1 into 5 divided by 2. Simplifying this further, we get minus 2 plus or minus 4 minus 20 is minus 16 divided by 2. So z is equal to minus 2 plus or minus square root of minus 16 is 4i divided by 2. Therefore, my z is minus 1 plus or minus 2i. If my roots are simply like z equal to 1, z equal to 2, z equal to minus 1, etc., I can take my roots directly and I will solve the problem. But here, the roots are complex. To make the problem simple, I am assuming z equal to minus 1 plus 2i as a, z equal to minus 1 minus 2i as b. So z square plus 2z plus 5 can be rewritten as z minus a into z minus b, because a and b are the roots of the equation. Next we have to find the singular points. As we discussed in our earlier video, if my region is simply mod z equal to r, I can easily found my singular point lies inside the region or outside the region. But here in this problem, the region look like modulus of z minus c is equal to some r. So better substitute the singular point in z. If you get the value less than r, then say the singular point lies inside. If you get the value is greater than r, then you say the singular point lies outside C. This is very easy and simple. At first we consider the singular point z equal to a, that is minus 1 plus 2y. Now we have to substitute this in the left hand side of the given region. Modulus of z plus 1 plus I is equal to minus 1 plus 2y plus 1 plus I. Minus 1 and plus 1 get cancelled. We get modulus of 3i. We know the formula. Modulus of a plus ib is equal to square root of a square plus b square. Now we have to find the value of modulus 3i. So I can write this as 0 plus 3i is equal to 0 square plus 3 square. So we get root 9, that is equal to 3. Next we have to compare the calculated value with the right hand side of the given region. It is very obvious 3 is greater than 2. Therefore we say z equal to a, that is minus 1 plus 2i is the singular point lies outside C. Next we have to deal z equal to b, that is minus 1 minus 2y. We have to substitute this in the left hand side of the given region. Modulus of z plus 1 plus I, substituting the singular point, we get minus 1 minus 2i, 1 plus I. Minus 1 plus 1 get cancelled. We have minus 2i plus I is simply modulus of minus I. It is going to be 1. So we have to take only the values. Now compare 1 with the right hand side and we can easily conclude it is less than 2. Therefore z equal to b is a singular point lies inside C. So we found z equal to a lies outside C and z equal to b lies inside C. Next we have to write the key points. Write the singular point and then consider the given question as capital I. Now for simplicity, I am going to rewrite this as integral over C z plus 4 divided by z minus a into z minus b dz. Now we have to deal with the numerator. Numerator is z plus 4. It is polynomial and it is analytic everywhere and it is an entire function. Now we come to the denominator. I have two singular points a and b. Since z equal to b lies inside C, I cannot take this. But z equal to a is a singular point that lies outside C. So z plus 4 divided by z minus a is analytic inside and on the given region C. It is not analytic everywhere. We should be very careful on it. So I can take my f of z as z plus 4 divided by z minus a, and we can say z plus 4 divided by z minus a is analytic inside and on the given contour C. Next we have to rewrite the capital I. Here z plus 4 divided by z minus a is analytic. So I am going to take this to the numerator. Z plus 4 divided by z minus a. Since the singular point z equal to b lies inside, I am going to keep z minus b in the denominator. Therefore integral over C f of z divided by z minus b dz is my question. Next we have to compare this with Cauchy integral formula. According to the formula, the singular point is a, for us the singular point is b. So we can write this as capital I is equal to 2 pi I into f of b. Now we have to find f of b. We know that f of z is z plus 4 divided by z minus a. Now substitute the value z equal to b. We get b plus 4 divided by b minus a. We know the values of a and b. Just substituting here, we get minus 1 minus 2i plus 4. In the denominator, we have minus 1 minus 2i minus of minus 1 plus 2i. 4 minus 1 3 minus 2i in the denominator minus 1 minus 2i. Multiplying the minus inside we get plus 1 minus 2i. 1 get cancelled. We can rewrite this as 3 minus 2i divided by minus 4i. This is my f of b. Next we have to substitute this f of b in capital I. We know that capital I is 2 pi I into f of b, 2 pi I into 3 minus 2i divided by minus 4i. Now we can cancel this I and 2. So we have minus pi by 2 into 3 minus 2i is my solution. Even we can simplify further. Multiplying this minus inside, we get pi by 2 into 2i minus 3 is my final answer. You can see the typed version. Hope you understand, students. Next, for more clarity, we are going to solve one more problem. The question is same, only the region is changing. In the previous problem, the circle is modulus of z plus 1 plus I equal to 2. In this problem, it is modulus of z plus 1 minus I equal to 2. As usual, step 1, let us find the center and radius. Substitute the value of z, that is x plus iy, rewriting the real and imaginary parts and applying the formula, we get x plus 1 whole square plus y minus 1 whole square equal to 2 square. We know the general equation of circle. Comparing the values of a and b, the center is minus 1 comma 1 and radius is 2. Now let us draw the figure. Center minus 1 comma 1 and my radius is 2. So 2 points away, that is 1 comma 1. Similarly, here we can take this as minus 1 comma 3. So using these 2 points, I can easily draw the circle, shade the region and mark the radius. Next we have to find the singular point. In the previous problem, we have already found the singular point, that is a and b. A is minus 1 plus 2i, b is minus 1 minus 2i. And we can express z square plus 2z plus 5 as z minus a into z minus b. Next we have to check whether the singular points lies inside or outside. First let me take z equal to a, that is minus 1 plus 2i. Now let us take the LHS of the region, substituting the value of z in the LHS, that is minus 1 plus 2i plus 1 minus I. Cancelling minus 1 and plus 1, we get modulus of 2i minus I, that is mod I. We know that modulus of a plus ib is equal to positive square root of a square plus b square. So modulus of 0 plus I is simply 0 square plus 1 square, that is 1. Next we have to compare the calculated value with the RHS. It is very clear, 1 is less than 2. So we conclude z equal to a is the singular point, lies inside C. Next, z equal to b minus 1 minus 2i. Substituting the z value in the LHS, we get minus 1 minus 2i plus 1 minus I. Cancelling the minus 1 and plus 1, we get modulus of minus 3i. So modulus of minus 3i is square root of 0 square plus minus 3 whole square. We get 3 again. Now comparing 3 with the right hand side, it is obvious 3 is greater than 2. So we conclude z equal to b lies outside C. Next, step 3, we'll write the key points. Consider capital I as my given question, and we know that z square plus 2z plus 5 can be rewritten as z minus a into z minus b. At first we take the numerator. We see z plus 4 is polynomial. It is analytic everywhere. It is an entire function. And now when we come to denominator, z minus a lies inside, but z minus b lies outside C. So it will not affect the problem. So I can write z plus 4 divided by z minus b is analytic inside and on C. It is not analytic everywhere. It is analytic in the given region, capital C. So we will assume this as f of z, and we conclude f of z is analytic inside and on C. Next we have to rewrite capital I. Since z plus 4 divided by z minus b is analytic, I will take this to the numerator. Since the singular point z equal to a lies inside C, we will keep z minus a in the denominator. Rewriting this, integral over C f of z divided by z minus a dz. Next, we have to compare this with Cauchy integral formula. In both the cases, we have the singular point a. So capital I is equal to 2 pi I into f of a. Next, we have to find f of a. We know that f of z is z plus 4 divided by z minus b. Substituting the value z equal to a, we get a plus 4 divided by a minus b. We know the values of a and b. Substituting here, we get minus 1 plus 2i plus 4. In the denominator, we get minus 1 plus 2i minus of minus 1 minus 2i. Simplifying this, we get 3 plus 2i in the numerator. In the denominator, we have minus 1 plus 2i plus 1 plus 2i. We can cancel this minus 1 and plus 1. Simplifying this, we get 3 plus 2i divided by 4i. Next, we have to substitute this f of a in capital I. Capital I is equal to 2 pi I into f of a. So 2 pi I into 3 plus 2i divided by 4i. Cancelling I and 2, we get the answer pi by 2 into 3 plus 2i. Therefore, my final answer is capital I is equal to pi by 2 into 3 plus 2i. In this session, we took a different problem. My singular points are complex as well as the region is little different. Hope you understand, students.
Thanks for watching. Hope you found this video helpful. Subscribe to our channel and share it to your friends. See you in the next video. Bye bye.